Hi everyone. I hope you can hear me right. Hello. Wonderful. So hello guys. Myself Sanjay and with Sahil. So today we'll be taking a session on computer vision basics and real-time object tracking in robotics. So let's get started. So first, in this session, what we'll be seeing is about what is computer vision, some basic introduction about computer vision, and we'll be seeing about software technologies which are involved in which are useful for computer vision, and we'll be seeing about the most common free source library OpenCV, and we'll be just implementing some basic functions in Python, and we'll also be doing some object detection, and we'll also be using ROS2 for integration with OpenCV, and which we can use it for real robots. And after that, like we'll also be seeing about training a model in YOLO and deploying it in the Python code. So starting with the introduction, like computer vision in robotics, like it means we have a robot which can sense things in the environment, and it should be able to perceive the things, and it should perceive the things, and it should be able to process. So like in kind of like it should be able to detect the object. So and it should do some real time action, like action in the sense to in the sense from what it had got from processing. So like if a robot is there, like it should be able to pick an object, like it should first detect something. So detect something, and it should process the object, and it should be able to pick. So for these kind of applications, like computation is more useful, and in industrial application, like computer vision is more useful. Like in the sense, like if we see in manufacturing industries, like instead of humans, robots are more in need nowadays. So robots are used for detecting defects in the manufacturing process, or it is also being used for manufacturing process. And the main thing, like now it is more trending one, that is ADAS cars, so autonomous driving vehicle. So what is that, like it should be able to detect the environment, and it should be able to sense things in the environment. It should be able to like it should move safely, like it should not dash anyone, or it should not hit anywhere. So like computer vision, like it is will be useful for sensing the real time environment. And with this, like we can implement computer vision with cameras and lidars also. So cameras will be an important thing in ADAS cars. So then next comes the this is nothing but human interaction robots, like where like the robots will be able to interact with the person by like just judging their emotions and facial expressions. So for that, computer vision is useful, and it is also being used in warehouses, like for picking an object from one place to another place, like for just tracking things in the warehouse environment. And also like it is being used in agriculture for seeing for the like ripened crops or not. And again, most useful for detecting faces, like the biometric scanners which we use in our mobile phones or laptops has a computer vision, like where it detects features in your face, and it just checks with the features of your face. Yeah, someone. Okay, so in facial detection also, like computer vision is more useful. And coming to this part, like this is nothing but we are using computer vision to just check the so like Like, you guys can put in chat also. So, and computation also useful for surveillance. So for surveillance in streets or stuff, like for any kind of suspicious activities, like we can use computer vision for just checking for the activities of the person. So in that case also computation is more useful. And then coming to the next part, that is about different softwares and libraries that are available for computer vision. So first comes the uh, most open sourced one, and it is OpenCV. And OpenCV is a free library and which is being used for image and video processing. In the sense, like we are having kind of some old black and white video, and we want to convert into some HD clarity video or image, we can use OpenCV. Like it has a lot of process and steps. So like we can use it for image and video processing, and like basic kind of image processing, in the sense like you can just add some filters like blur, which will be seeing in the session. And also like OpenCV is used for object detection, and we'll also be doing this in the session by just detecting a object with a kind of threshold and stuff. I'll be explaining that in the next few slides, and the Python script. And Python script is also like OpenCV is also used for feature extractions, like in the sense for feature extractions, like in a face, like it should be able to detect nose and mouth. For that also, like OpenCV is being useful. And for camera calibration, like for camera calibration, in the sense for a robot to be able to detect in the environment, we should calibrate the camera, like in which angle it is and how it should perceive the object. So for this, like we'll be using OpenCV. And here, like if you guys didn't understand what is feature extraction, like if there is a bike, it should be able to detect wheels and handlebar and like kind of shaft or engine, and it should be able to detect these mirrors. So these are kind of features that the model should be able to detect to just judge it as a bike. So, and the next comes the TensorFlow, and this is also most important not library, like it is a library, like it you can train models with this, like you can train and build image classification models, and you can also do object detection, and you can also do image segmentation. Image segmentation is nothing but like in this image, like you can see it has classified each object, like building into some colors. And this environment of a road, like you can see a person who's standing here, and there is a biker and there are some cars. So like it is able to classify the environment as cars and buildings and people and bikers, so etc. For this is nothing but image segmentation. We can do this in TensorFlow. And next comes the PyTorch. So PyTorch is a deep learning library, and it is being more useful for image recognition and natural language processing. So like in the sense, image recognition, like if you are giving some environment, should be able to detect detect things in the environment. It should be able to like give a real time description of the image. For that, like you will be using a PyTorch. And this is scikit-learn. Like it is more kind of mathematics kind of library. Like it is being used for simple uh, image filtering and color manipulation and geometric transformation. So in the sense geometric transformations, like if you guys want to understand like more easily, like it is nothing but if you have some kind of vehicle, like environment like this, you should be able to transform this image such that you get kind of bird view, like on the top view. So these are nothing but geometric transformations. Like you can do this all with scikit-learn. You can do this like things with OpenCV. Like it is more advanced nowadays. So like you can do these things with OpenCV itself. And after that, like uh, we're also Keras. This is also an important deep learning library, and which is built with TensorFlow only. And it is just as, like it makes it is makes a job easier for creating models. And for that, like Keras is more useful. And YOLO, like it is also created with TensorFlow and Keras. And it is like you can just you can just train a model in just 5 lines of code. So it makes your job so easy. So like we'll be Sahil will be discussing how to use YOLO in the few slides. And These are some basic things which are being useful for robotics, like ROS and Gazebo, which we have seen in previous sessions. And MATLAB is also an important software for image processing, and like it is being useful for creating plots and stuff. And for that, like MATLAB is also like has a kind of library for computer vision and image processing. So this is about softwares and libraries for computer vision. So now let's just come to convolution. Like convolution, like I'll just explain what is the need of convolution first. Like first, it is being useful for computer vision, like for image processing things. Like it is kind of mathematics, like a kind of operator in mathematics, like addition and subtraction and multiplication. Like it's a kind of operator. So like I'll just explain some overview of that. And like it is convolution is useful for extracting features in the image. Like in the previous slide you have seen, like for having this bike, like you want to detect a wheel separately, and for detecting wheels, like you should do something, some kind of operations to detect the wheel. So for that, like we should use convolution. And like for detecting each and every part of the object, like we should do convolution with different kernels. So I'll explain you what is kernels. So it's also being useful for detecting objects and track movements and recognize patterns. So like we'll be like OpenSea, almost all the operation uses the convolution operation. Like we'll be using just a single line of code, but that will be done with convolution and backend processing. So this is just an overview of convolution. So let me just explain you what is convolution. So for that, first assume that we have two signals, like this be an input signal F, and this be an impulse response, it's called as G. Okay, so first, like we should be the first kind of thing which you should do is flipping this impulse response signal, that is G. Okay, so after flipping, and we should be moving this impulse response to like kind of minus infinity. Then what we should do is like we should do element wise operation, like element wise multiplication at each and every parts when you're sliding from minus infinity to plus infinity. So here, if you see like this this region, like it is not from the last, like it is just a part in middle, so that we can understand like what operation is going on. So first, like let's take in this x-axis, like we have some values out here, and at -2 in x coordinate, we have a value of 0 in both the places. So we'll be multiplying 0 and 0. Then we'll be just moving to the next question, like -1, and we'll be having some value out here, like 0, comma 0.25. Again, we'll get 0. And like here, if we come to at x coordinate 0, we'll be having the f value as 2, and a g value as 0.5. So we'll be getting kind of 1. So while doing this convolution, like we are just multiplying each and every element at a instance. Then what we are doing is then we are summing up all the element wise multiplication and adding it to get some value. And that value is nothing but the resultant out here. Like in this, like for the value at like to get the value at 0, you are just taking the this instance and multiplying. So similarly, like you will be moving from minus infinity. In this animation, you will be able to see like we are just moving the this is called as impulse response. We are just moving the flipping the impulse response and moving it from minus infinity to plus infinity. Here, like for demonstration, it's being starting with -4. Like you will be usually doing it from minus infinity to plus infinity. And but in computer vision, like we can't practically explain what is infinity. For the practical purpose, like we'll be having the maximum binary digits, so that like for making the calculation more simpler, instead of going to minus infinity plus infinity, that won't be feasible in computer processing. So for that, like uh, just the process, like just to summarize, like first we'll be flipping the impulse response, then we'll be sliding the impulse response from minus infinity to plus infinity, and then at each instant, what we'll be doing is we'll be doing element wise multiplication with the corresponding x coordinates, and we'll be just summing up the product. Like we'll be just summing up the products which we got in this multiplication at this instance. Then after that, like we'll be just getting that as an output, and we'll be just storing it as a f of like f star g is equal to a convoluted function like called as h, and we'll be storing the values at h of 0 as this the result which we get after summing up the product. And finally, like we'll be just shifting for each and every instance, and we'll be getting the output function like this. So I hope you guys got it, like what is convolution. So now coming for a convolution in like images. So what is happening here? Like before that, like I just want to explain what is how the image is being stored in like computer like image processing and stuff. For that, like when we have a kind of image like this, so each and every pixel will be having three colors like BDR for like for getting the colors, like for each and every pixel. For having kind of black color, we should be having all the BGR values to be 0. So like for that, what happens is you guys like no like what will happen is like for black color, all these values of BGR will be 0, and for each and every pixel, like if it is red, it should be like the red value should be more. Like the maximum value for pixel to store is like 0 to a value between 0 to 255, and 0 is with 0 intensity. Like it will be in black color, and if it is a maximum intensity of 255, it will be red in color. So for that, what will be happening is for storing this red color part, like we'll be having this kind of reddish pink. So we'll be having some red color with some very little values of blue and green, and with more values of red. So like here, red will be something around like 200 or something, and green will be out some 30s or 40s, and blue also will be some 30s or 40s. So we'll be getting kind of color like this. So, and for here, green color, it will be more for green color and less for red and blue. So like this, like, and we'll be getting this image into an array. Like this, if we consider this image as 256 pixels into 256 pixels, like we'll be getting an array of 256 pixels and 256 pixels, and we'll be getting three channels. Like it will be 256 into 256 into 3, a kind of numpy array. So we'll be having an array like this. So we'll be using this array for image processing, but um, already we saw this convolution operation is more heavier. Like we can't use it for three channel. It will be more complicated. Like for that, what we'll be doing is for creating the operator to be simple and more time efficient and space efficient. What we'll be doing is we'll be converting this BGR images into grayscale image. So in this grayscale image, what like it's nothing but just averaging these BGR values, and we are just getting a value between 0 to 255. That will be the intensity of like if it is full 0, it will be like if it's fully black, and if it is white, the value will be for 255. So now we have converted this BGR image into a single channel image. Like we just average these three values. Like for example, for the first pixel, like we'll be just adding 20 plus 9 plus 4 and divided by 3, and we'll be getting the value of the first pixel. So with this, like we're creating grace. So you can just see it out here, like the grayscale images will be stored like we'll be having a values, and like this will be just a 2D array. So we convert a 3D array into 2D array, and we made our job more time and space efficient, and reduce the time complexity and space complexity. So this is the reason for creating a BGR image to grayscale image. So now we'll see like convolution in images. So for seeing what is like how convolution works for images, like we'll be having a kernel like this. Like the impulse response which we have seen here is called as a kernel out here. So this is a kernel. Like we'll be also having a 2D kernel instead of a single dimensional impulse response in signal processing, and we'll be having a kind of kernel like this. So with this kernel, what will happen is like you should be you'll be just passing this like kind of same like first we should flip the kernel. Like it doesn't matter out here. We are not flip the kernel, like flipping the sense X and Y coordinates will be changing, but we don't use it much. We'll be having more symmetric kind of kernels only. That's why like we'll be getting proper image processed output. So we'll be using mostly symmetric ones, and in few cases like we'll be using something called as correlation. Instead of like we'll be just avoiding this step, and that is called as correlation. Like that doesn't matter. Like we'll just deal with convolution. So first like we'll be just flipping the kernel. Like here it doesn't make any sense. Then we'll be sliding the kernel. So first is like sliding the sense like we'll be first keeping the kernel in the first position, and then we'll be doing element wise multiplication. So like what happens is like you should multiply 21 into minus 1, and minus 1 into 19, and minus 1 into 17. So like, and we'll be multiplying each and every values like minus 1 into 71, and 8 into 76, 73 into minus 1, and 153 into minus 1, and 164 into minus 1, and 164 into minus 1. We'll be just multiplying each and every element with the corresponding elements in the kernel, and we'll be just getting output. Like after uh, doing element wise multiplication, we are just summing the products which we got, and after that we'll be getting a final sum as minus 74, and we'll be giving the value for this pixel in the output image. So and after that, like what we'll be doing is we'll be shifting like for each and every pixel, like we'll be just sliding the kernel, and we'll be just getting each and every output. So like first, if you see, like we are getting an output out here, and we are just storing it here. We are getting output for this 3 into 3 uh, part of the image, and we'll be storing it out here. And like you guys can think like what is like when we do some kind of operations, like we'll be getting same kind of image. We won't get a image that is being shorter. Like if we have some 100 into 100 pixels, like we won't, like if we do this operation, like you can see like we'll be just focusing on this kind of image, and we are missing some data out here. But this doesn't happen in like when you're using convolution, like some kind of operators in Python. Like that is because like like while doing uh, convolution operation, like what will happen is this, like if you have kind of uh, 3 into 3 image, like we want to get an output as 3 into 3 image only. We should not get something like 2 into like 1 into 1 or something. That will be like we it won't be useful for us. Like, and we'll be missing some data. Further, what Python does is like it'll be just creating a extra layer. Like if the image is 3 into 3, it'll be creating extra outer boundary, and to make it as 5 into 5. Like it depends on what this kernel is. If it is 3 into 3, like we'll be just using this, like we'll be just using it as like if it is 3 into 3, like what will happen is like we'll be just we won't miss any data, and we get the same 3 into 3 image while doing this padding. So that's what will happen here. Like so I hope you guys get it. So here, like we'll be seeing how like this convolution is being used in image processing. So I'll just implement all this in Python text in the Python script after this like slides. So first, like we'll be like like first job is for us like is to blur an image. So we'll just start with from here this blurring part, and it'll be more easier to understand for you guys. So we have a image in the left part which is more sharpened, and we are having a blur image by just passing it with this kernel. So for blurring an image, we'll be using kernel kind of low pass filter. Like it should be averaging the values out here. So in the sense like if you are getting, just assume this part, like we are be having a like assume like 9 pixels. Like we should be taking this region like we should take the first 3 into 3 cell. With that, like we'll be just doing element wise multiplication. So with doing this element wise multiplication, we'll get some output value which will be a resultant of all the neighboring pixels. So what happens is like ultimately like we are reducing the intensity at that location, and we'll be getting more blurry image. So that is what like we'll be using this kernel, and we'll be doing the convolution operation in image processing, like moving it from each and every part, and we'll be just sliding it through the image, and we'll get a output as a blur image like this. So also note like we should not always use into one into, like doing this will not average, like it will just add up. So we should be dividing it by 9. For that, like we'll be getting the intensity proper, like or else like we'll be getting the pixel value more intenser. Like for that, like we should always multiply value with like a 1 by 16 after doing, like in this kernel, like all the values will be like like will be normalized. Like the sense will be 1 by 9, 1 by 9, 1 by 9, and 1 by 9. So this should be more like it should be, it is a note like here in this, like we won't be doing all this convolution in Python. Like we'll, for this, like we have just a comments in Python, like in OpenCV, and we'll be just using it directly. So we won't bother much about this convolution operation. So just to have a knowledge, I'm just explaining it. And this is another kind of filter. Like this is called as Gaussian blur. So you guys can see like there is some difference between these two images. Like here, like we can, while using this Gaussian filter, like it'll be having a kernel like uh, I just show you in the script, like it'll be kind of a dome shaped thing, like where we'll be having the center pixel value more intense, and all the neighboring pixel less intense, and all the farther ones more less intense. So like with this while doing this Gaussian blur, we can easily detect edges. So for that, like we'll be doing this blur to just to extract feature. Like if it's more intenser image, like we can't get the edges more easily. So for that, we'll be using blur always, and we'll be preferring mostly a Gaussian blur. So after this, like we'll just move to edge detection. So in edge detection, what is happening is like we should be able to detect a change. So if you assume this flower, so this flower is a full like it has colors of orange and yellow, and here it is of fully like kind of black and gray. So we should be able to detect the edges out here. So for detecting the edges out here, like what you should do is should pass a, like it is again a convolution operation. Like what happens is like with this kind of kernel, we'll do is like we'll be trying to get for the difference. If there is any kind of difference, we'll be getting a positive value, or like if it is same, like we'll just cancel out all the values, and we won't get any values, and we'll be getting 0. So with the 0, like we'll be getting all this region as black. And if we get any kind of difference, what will happen is like we'll be getting some positive intensity, so that we'll be getting some kind of white color. So with this, like if it is same, almost similar intensity, it is having similar intensity, the things will get cancelled out. So if it is kind of all 255, 255, you can just assume for simplicity, you'll be getting a fully black region out here, because while multiplying minus 8 into n for n 8 times, and when multiplying 8 into that intensity n, all things will get cancelled, so you're getting a zero intensity image. So that is what happens in edge detection. Like we should be able to detect the change from this black to this orange. So with this kernel, you'll be getting this kind of edge detected. So I'll just implement this in a Python script, so you guys can understand more good. So, and this is like sharpening the image. So what does sharpening mean? Like in the sense, if we have any kind of image, like if it is kind of blurry, we should be able to sharpen it. In the sense, like it should be more attractive. Like it should be like like kind of more intensive with respect to the nearby pixels. So like if we have kind of pixel out here, so like you can just see like this is kind of more blur, and this is kind of more sharp. So in sharpening, what we have to do is like we just make this center like the pixel out here to be more intensive with respect to other nearby pixels. So we feel that the image is more sharpened. So for this kernel, like we'll be having a kernel where we'll be having like here everything will get cancelled out when you just add it, and here like what will happen is like you will be getting some positive extra value. With that positive extra value, you'll be able to detect the sharpened image. So this is about like convolution in image processing. So then like we'll just start with the Python script, and so I'll just discuss like OpenCV again, so open source computation library, and it is being used for image processing and machine learning integration. And so what we'll be going to do is like we'll be just trying the OpenCV function, basic functions blurring, thresholding, and stuff which you have seen here, sharpening, using Gaussian blur and edge detection, etc. And if you guys are more interested in learning OpenCV, you can just go to the official documentation of OpenCV and you can just learn. So I'll just share my Python script. So I hope you guys can see the Python script out here. Like first, I hope you guys would have installed Jupyter Notebook, or you can also use PyCharm. Like for PyCharm, you won't be able to get outputs running the code and outputs. Like you should run it separately. So if you have having Jupyter Notebook, it will be good. So also use Google Colab without installing anything. Like you can just go to Google Colab and use this. And so before starting, first we should be able to import libraries. So if you guys just run this command without installing OpenCV, we'll be getting some kind of error. For that, we should install OpenCV. This is the library which we'll be using, and for installing each and every library, you just enter the library name out here. In this case, we want to install OpenCV Python, so we can just install OpenCV Python. If you want to install NumPy or Ultralytics, just use pip install and install the libraries you want. So we'll just see how to uh, how the image is being stored in the Python thing by OpenCV. It is just stored as an NumPy array. So I guess you guys will know what is NumPy array, and it's nothing but kind of list. So most for sake of simplicity, you can call it as list, but it's not actually list. So you will be storing all the values out here with let me just run this. So first, we are having an image mobile. So it is so this is the image. So with this image, we'll be with this image, what we'll be doing is we are seeing how these image is being stored with the intensity values, and as I have explained the slides, right? How the BGR values are stored. The same thing applies here. So here this image is being stored uh, kind of 3D array. So the shape of the array is this shape is a function NumPy library, and this is being used to detect the list, the array size. That is the images of 605 pixels in x-axis and 19 in x-axis and 605 in y-axis, and it is having three channels. So an array, the image is being stored in Python. So after that, we'll be having this array. So with this array, we want to we can't just see this array. So to just make this array into an image, we'll be using a function called cv2.imshow. So this will be the first thing is this mobile phone is nothing but the name of the window. So this will be the name of the window, and this wait key is nothing but for how much duration you want the uh, the displayed image to be there in the screen. This wait key is being useful for that. Inside this wait key, instead of zero, you can pass anything if you pass any number, it'll be staying in the screen for these many milliseconds. So if you give it as zero, like I don't stay for 0 seconds, no? It'll be staying for infinity. As long as you don't press any keys in the keyboard, it'll be staying in the screen. And this destroy windows is a function which is useful for like after this wait key is over. Like it is a kind of uh, delay function in like this is kind of delay function. Like after this delay is over, like the CV2 will destroy all the windows with this function. CV2 dot destroy all windows. So if I run this, like, oh sorry, I guess you guys can't see it. So I guess you guys can see the window like this is CV2 dot imshow function. Like with this imshow function, we are getting a window named mobile phone, and this is the image. Image is nothing but this is number array. So we are just with this with these few lines of code, you will be able to display the image, and after like with displaying, you should be able to do some processing. That is what the ultimate goal of OpenCV is. So first, like we'll just like see some basic drawing lines thing in OpenCV. Like first, like for seeing this, like for drawing a line in this image, like, in this image, like what you should do, like first for drawing a line, we need a start point and end point, and we need color and thickness. So for that, what we're doing is like I just do this one, and I'll just run this and I'll show you guys. So we got a line like with this line function we are able to draw a line. So this is nothing but and if I were to mention one thing, like in OpenCV, like what the coordinates of the image is different. Like it's not like this will be the y-axis and this will be the x-axis, but instead what will be happening is you will be having this like your origin will be out here where my pointer is, and this will be our origin, and here like this will be your x axis. So this being your x axis, and this will be your y axis. So like your y axis will be like inverted. Like it will be instead of like the negative y axis in your geometry coordinate will be your positive y axis in your image processing coordinate. So having this in note, like we are just specifying the start point of the line function here. That is nothing but 400 comma 250. So 400 in x-axis and 250 in y-axis. So this is the start point which we are specifying. And next is we are specifying 300 comma 30 as your endpoint. So this is 300, like this is 300 in x-axis and 13 y-axis. So this is nothing but color. Uh, like we are just specifying the color in terms of uh, tuple. So this like it is a BGR format where 255 is your maximum blue intensity and 255 is your maximum green intensity and 0 is your red intensity. So like when green and blue are mixed, you'll be getting a color like cyan. So this you'll be getting in this color, and the thickness will be of 5 units. Like 5 segment 5 pixels. Like the thickness of the line will be 5 pixels, and the next function is circle. So again, like I'm just copying the image out here, and I'm just passing this numpy array again here, and with this like here like this is nothing but the center of the circle. Like here 360 comma 200. So 316 x-axis and 200 in y-axis. So this will be a center of the circle, and the radius is nothing but 100. So like it will be 100 pixels, and the color of the circle which you are specifying is 255 comma 100 comma 0. That is like 255 in maximum blue and a little bit of green, so you'll be getting kind of greenish blue or stuff. So and the thickness is 5 pixels. So again for a rectangle function, we are just passing the numpy array of the image, and we are just specifying the this is like in for drawing a rectangle, we specifying the start coordinate and the end coordinate. Like we'll be specifying the two diagonal points. Like for drawing a rectangle, you can just draw with just a diagonal. So by specifying the start point and end point of the diagonal. So here, like this color CV2 in this for this rectangle what you're drawing is like the start point is 250 comma 200. So 250 in x-axis and 100 this will be your start point, and 450 comma 300 this will be your end point. And we are specifying the color to be green. That is green value is 255 out here, and the thickness is 3, so 3 pixels. So and for drawing text, I for- like here I put image like it should be copy because I'm just doing all the image processing with this copy thing. So I have to run it again like so. This text wasn't displayed because I used without like I just used this image, but I'm showing copy out here. So that's why I didn't get the text that time. So here uh, cv2 dot put text. So in this with this put text command, what will happen is like I first that's the first attribute is nothing but the text will be inputting as a string, and the second attribute is like you will be specifying the bottom left corner, that is this part of the text to be there. Like this also this text is will be in kind of like rectangle shape, so you'll be specifying the bottom left corner of the rectangle where the text has to be placed. So that's what this tuple is, and we are just specifying the uh, we are just specifying the font style. So CV2 just supports very basic uh, font styles. Like you can't use many font style. You can use just basic things. Like that more often used one is Hershey Simplex, and here like you in this like here you can specify any methods where you can get the font styles. Like there are many like Hershey triplex also something is there, and many are there. So and this is nothing but scale. Like font scale is nothing but how much you're scaling. So for that you'll be using this font scale, and this is to specify the color, and this will be cyan color, and the thickness of the text what you're putting is it should be 4 pixels. So this thickness is 4. So with the show function we are just showing the image, and we are just uh, drawing line and drawing these simple geometric shapes. So now we'll just come to grayscale conversion. I have told you like you should always convert a BGR image to a grayscale image for simpler and to the code to be less time complex and space complex. We'll be converting all the image to grayscale. So this is for converting to grayscale function. Like you can do this in many ways. Like while you're reading this image, right? That is like I'm just copying out here while reading in cv2.imread function itself. Like I can specify an extra attribute as 0. If you specify that as 0, you'll be getting a grayscale image. That is an one more method. Here, like what I'm doing is I'm using a function called cvt color. So with the cvt color, what happens is like you're just converting this. Like you can just convert from one scheme to the other scheme using the CVT color. Like first, you can convert a color BGR image to a grayscale image, or you can convert a BGR image to a RGB image. Like you will be just doing some basic operations with the numpy array. Like for while using this color BGR to gray, we'll be just averaging all the three channels. So that's what will be done with this method in CV2 library. Like what we'll be doing is like we'll be just averaging it, and we can also do like we can convert BGR to hue. Like hue is another kind of scale. Like hue saturation is another kind of scale where you will be converting into different schemes. So for that, like you will be just specifying different methods out here in this attribute. So that's what we'll be doing. So I'll just show you guys. So here you got two images. Like this is the input image which I'm giving it, and this is the output image. So here what happens is like you are just converting it to grayscale image. So nothing much big. So I'm just giving some random to close the image. Then after this, like now comes the blurring. Like we are seeing what is Gaussian, right? So the Gaussian kernel will be something like a dome shape, and will be having a 2D array with all the weights having the weights will be more at the center, and it will be decreasing as we move away from the center of the kernel. So this will be the Gaussian kernel. So for using Gaussian blur, what will be passing is first is the image, like this image is nothing but like you will be passing an numpy array. Then after that you will be specifying the kernel size for Gaussian blur, like like and mostly we'll be using like we should always use odd sized kernels actually. Like you even sized kernels. Like this is an important thing to note. Don't use even types. You'll be getting error because like while using like you when you use uh, like even sized kernels, you can't get a proper image. It won't be blurred. It will be like worsened. The image will be worsened, and you won't get proper symmetry in the image. So you'll be losing all your data in the image. So like, and if you can just try with the convolution operator which I have taught you. Like you can just try some example by taking 3 into 3 and even kernel and see. So and this is nothing but and you should always use odd sized kernels like 3 into 3, 5 into 5 out here. So this is like sigma x. Sigma x is nothing but standard deviation. Like this is being useful for expressing the slopes, like how sharpened this Gaussian function should be. Like it should be more steeper or it should be more flattened so that like it, like if it is more steeper, you will be getting like the blurriness will be more or less, and if you making it more flattened, the blurriness will be increasing more. So with this sigma and sigma x and sigma y, you'll be specifying the blurriness of the image, and this is border type. Like border type and this you won't be using much. Like this used to specify the border type, like how sharpened the kernel should be. Like in while after doing convolution, you'll be having a border, right? So how should that be? For that, you will be using a border type, which you won't be using normally. Like we'll always go with the default one. So here, like I just converted the image into grayscale image using a CVT color. And after that, I'm just converting it to Gaussian blur. Like uh, I'm just passing a 5 into like I'm just specifying the kernel size to be 5 into 5. Like as you increase more and more the size of the more like the larger the kernel size, like you'll be getting more blurry image. So if it is less, like the kernel size is so like 3 into 3, you will be getting very minute changes. And if it is 5 into 5, you'll be getting some visible changes. If you do some uh, 11 into 11 or 13 to 13, the image will be more blurry. And if you use like kernel says like 21 into 21, will almost lose all the data in the image. So we'll be just uh, co- using Gaussian blur for a 5 into 5, like 5 into 5 kernel. And this zero is nothing but to specify the default values, like all the sigma values of a like a standard Gaussian function. Like for that, like if we provide as zero, we'll be having the normal standard deviation as 0.66 in a Gaussian function, and then like all this border type will be taken as default. So after that, like we are just showing the image. So here, like if I run this one, like you can see. So this is the original image, and you can see a kind of blur. So the more advantage of this Gaussian function is you won't lose your edges. But if you use normal box filter, which I have shown in the slides, like 1 1 1 in all the places of the kernel, you'll be losing your edges. So the advantage of using Gaussian blur is you won't lose your edges. So that is some advantage part of Gaussian function. And next, we are coming to edge reduction. So as we have seen the kernel out there for edge reduction is something similar to this. So what is in CV, like for doing edge reduction, we'll be using a function called clanny. So in this, like what is happening is like we are just passing an image function, and we are just specifying the threshold values. Like the threshold is nothing but the value which we get after doing this convolution. Like it is nothing but uh, threshold one is nothing but lower threshold for an edge intensity, like in the sense like how intense the edge should be. Like the difference which we get if you are moving from black to orange, we'll be having kind of more intense red. Like if you are moving from red to pink, we'll be having less difference. So that difference we are specifying the threshold one, that is lower threshold, and we'll be specifying the upper threshold as threshold two. And this aperture size is like it is useful for a sawable operator. Like we'll be trying to detect the features in vertical and horizontal, like in vertical direction and horizontal direction. We won't be using now. Like this is also an important operator which we use for feature extractions. For like we have seen an example of bike for detecting wheels. We can use sawable operator, and further we'll be specifying the aperture size and gradients. So. Uh, So coming to basic thing, what we're doing is in CV2 any grayscale image, like we're just specifying the edges to be like the lower threshold to be 100 and upper threshold to be 200. So this number can be between 0 to 55 only. Like uh, and make sure like you just give the lower threshold to be twice or thrice of the upper threshold. Like if you're not doing that, like you want it proper kind of uh, edge direction. So better to use with the lower threshold to be like twice of lower threshold to be the upper threshold. So I just run this snippet and show you. So here you guys can see like I'm able to detect the edges. So of high I'm able to detect the edges because a huge change. So here like I'm not able to detect the edges. Like here it is more blackish color. So it is more blacker gradient. So the difference is not sufficient to detect it as an edge. So here we are using like we are not able to detect the edges out here, so the region is fully black. When you're getting the value between the threshold values, the output will be stored as a higher intensity, that is white, and will be detecting it as an edge. So if we are getting the threshold, like if you are putting the threshold such that when the image, like when we are having the threshold between 100 and 200, we'll be able to detect for a change, and we'll be getting a value to be 1 in the when it is between the threshold is between the upper and lower threshold. And with that, like we'll be able to detect for an edge. So here there is a small difference because of the wood wood's texture. So we are able to detect some random noises out here, and we are able to detect the mobile phone's edge also. So this is what edge is about, edge detection. So now let's move to thresholding. Before that, okay, okay, then we'll move to thresholding. So for like in thresholding, what's happening is like we are just I'll just show you guys an output, and you guys can easily understand. So like you just see this, like in this we are just trying to detect from mobile. So here what we are doing is like first we are converting to grayscale image and we are detecting edges. Like this is just for the sake, like we are using it again. So and here like for a threshold, what we are doing is like we are applying the threshold. So thresholding is nothing but uh, if we have some image, like that is we are passing this image out here, and we'll be just passing the threshold value. Like the threshold value is like if the threshold intensity at that location is something as if you provide it as number, and like if all the intensity of the region is above that threshold value, like you'll be able to detect for a change. So if it is for max value, if you see like for max value, it is nothing but you are just like in an image, like you're specifying that color to be what, like if it is for the value to be assigned for the pixels which are above this threshold value, like we'll be just giving us if you give this value as 255, you'll be getting white, and if you give something like 100, you'll be getting some grayish white. So that is what will be happening in this like we'll be passing in max value, and this threshold type is nothing but the method. Like we can what you've done out there, like if you guys see like what you're doing is like when it is above this threshold, we are just giving it as white, but if it is below this threshold, it is black. But in some cases, we might need this to be like uh, the color should be changed. So what we'll be doing is like we should be able to detect for like you should just inverse the binaries image. For that, you can use like the threshold type to be CV2 thresh binary inverse. So all these things are like I'm just using it here. So the grayscale image and the lower threshold is 33. So I want to detect just the mobile phone, so that I'm just using the image to be like the threshold value to be 33, and the like I should display the thing which I detected with full white, and I'm just using a CV2 dot thresh binary, and I'm just running this. So you guys are able to detect all the like places where the intensity is above 33. So all these are white, and it is fully black out here. So the intensity is obviously less than 30s. So we'll be just detecting this mobile phone. So in case like if you want to detect for in like use inverse, like they're just inversing, like all the black regions will be white now and the white regions will be black. So if I run this, so now I'm just able to detect for a mobile phone. I just masked a mobile phone out here. So this is what thresholding does. So next, like now we'll just try to do some contours, like
అదేంటో
contours.
ఆ ఇంటి దగ్గర వైఫై ఫోన్‌కి కూడా రాదు. అదే అసలు ఎంత స్పీడ్‌గా ఉంది.
Hello, I didn't get like, okay. So we'll be using contours, like contours has some, like it is also a kind of operation where we'll be trying to detect for an edge, like it is not kind of face detection. We'll be getting more good advanced version of edge detection. So with this contour, we can also use we can mask the image. So which I'll be using it out here. So for contrast, like first is image, and this will be retrieval mode. Retrieval mode is nothing but like you should be able to detect for the outermost boundaries of the object, and you should also like this approximation. This in this retrieval mode, like you can just specify, like if you're having a hollow object with kind of cello tape, you'll be having an outer edge, and will be detect two edges. Like that should not happen in the sense like you can use RETR external, like where you will be able to detect just the outlines of the object. So and with this RTR list, like you'll be getting all the inner and outer contours. So this is nothing but approximation method. Like approximation method is nothing but we'll be trying to like if in simple, like we'll in chain approx simple, like we'll be just taking few locations where more change in direction is observed. So in this chain approximation, we'll be storing all the points, and this will be more like we'll be utilizing more memory, and it'll be slower in processing. So for drawing contours, there is a function called CV2 dot draw contours. So contours is nothing but they just like I'll just show you in the snippet. So here like for we'll be just using contour index, and we'll be using it -1 because it should be default. Like this is nothing but like which contour you want to specify. Like it should be inner or outer contours. We use this contour index, like that is light and color. Like we'll be just so like for this like for drawing contrast, like we'll be specifying the color in BGR value, and this alpha is for transparency. So how like if you give a 128, it will be half transparent, and if you give 0, it will be like you won't be able to see anything. Like if it is 255, it will be more intensive. So that is what we'll be using this uh, fourth value in the tuple. So and this line type is nothing but how sharpened the line should be. Like if it is like 8 contrast connected, it will be done with CV to the line 8. Like it will be kind of eight lines connected together, and this will be like you will be able to detect like breaking things. Like you won't be able to smoother one. So for getting a smooth one, you can use CV2 line AA. So you'll get smoother lines out here. And this is nothing but hierarchy. Like hierarchy is nothing but like the information about the contours, like how it should be. Hello. So like we'll be just using this hierarchy for like getting what contours to be displayed in the image. So this max value is like you're just specifying maximum level of hierarchy. Like that is all. Not, we won't be using much because like we'll be giving these values to be default mostly. So for I'm just using converting to grayscale image. I'm just doing thresholding, and I'm using the find contrast function like to find the contrast in the image. And you guys can see like uh, this will be the array where the contrasts are being stored. And this hierarchy is nothing but like what kind of context has stored. Like it is like we'll be having 0, 1, and 2. Like where 0 will be for outer contrast and 1, 2 for the inner and outer like inner contrast. And for that like we'll be using hierarchy. Like that is we won't be caring much about this hierarchy. Like so here when you like we are just drawing the contrast using this contrast. Like we are just deducting like we are just uh, like on which image the contour should be drawn. I'm just passing that image compare array, and I'm just putting the contours array which is being deducted with fine contours, and I'm just giving -1 for default values. And this draw contrast 255 255 comma 0 is for drawing the like in which color it should be. So this again BGR like it will be cyan color, and this 3 is for thickness. So if you guys see, if I'm just running this code, so we are just getting the contours out here. So it has a lot of noises out here. So further, I'm just specifying the area. So for specifying with area, like what I'm doing is, mm, I'm just giving the contour area to be like, I'm just giving the area limit to be 1000 pixel square. So here, like you can see bounding, you'll be drawing the bounding rectangles with the contours you have detected. So the I'm just passing the contours like which are above like I'm just drawing the bounding rectangle first. Like bounding rectangle in the sense like uh, so you should be able to detect like draw a rectangle which is being surrounded by all the pixels out here in the contour. Like in the sense like I should be able to draw a bounding box out here. So and I'll be detecting all the bounding box for each and every contours. And now like I'm just passing like so I'm just mm, passing all the contour area which is above the 1000 area pixel square. So I'm drawing the contour area for so this like with this contour area to be above 1000 pixel square and just deducting those contour areas, and I'm just drawing a rectangle and just putting a text which you have seen the uh, basic geometric shapes in the first snippet. We are just using the same comments out here, and I'm just showing all the original image and thresholded image and the image with contours. So like with this, like you are able to detect for the mobile. So that is about using contours. And now we have seen all things with just like images. Like we should for tracking it is nothing but we should be able to detect for an object simultaneously for each and every frame. So that will lead to tracking. So for first like we'll just see how to uh, read a video in OpenCV. Like we'll be using a function called video capture. So with this video capture, like what we'll be doing is we should be able to detect for like uh, this video capture is nothing but just like this cap variable is storing all the uh, oh, are you speaking anything? Okay. So with this video capture, like what I'm doing is like I'll be checking whether the video frame is there. Like if the frames are being there in the image. So that is nothing like it is just a kind of true or false value. And I'm just checking whether the video is being open. So if it is not open, like I should be able to detect for like I'm just printing an error message and exiting. And if you guys didn't use this exception kind of thing, you won't like you'll your Python might get hanged, or sometimes your Python will be getting hanged. So it's better to use this exception kind of thing. And we are just reading each and every frame of the video, and with this red is nothing but a true or false value. If like if a frame is detected, return a true, and if it is not detected, it will be giving false. So this frame is nothing but each and every frames of the video. So I'm just running it in a loop so that I'll be getting each and every frame. So, and if there's no frame detector, I'm just printing no frames is there to be to read. So I'm just using this if condition to avoid unnecessary errors. So this like I'm just resizing the window frame like frame window with the resize function. Where I'm just passing the frame and just scaling it to this size. Like you can also use scale function like where you can just you won't miss the aspect ratio of the image. Like if you use kind of two uh, like a like two like a tuple with two values, you will be uh, changing the aspect ratio of the image. So I'm just running this thing like for so you guys can see a video which is being running out here. So I'm just running it as frame by frame, and I'm just using the things which you have seen for basic image processing out here. So a similar thing is for a video. Like instead of doing for like for an image, like we are just using for simultaneous series of images. So that is what like for which we are using for video capturing OpenCV. So like I just try to demonstrate the same thing which I've seen for image processing with um any issues. Okay, so like for you can use this CV2 dot video capture will be you can use your webcam also. Like if you give 0, you'll be getting your webcam feed, and you can use 1 for like using external webcam. So I'll be using this one to just show you guys like to detect for an image. So first, like I'm just running this. So you guys can see some external webcam which I'm running here. So I should be able to detect this object out here. So I'm just doing the same image processing out here. Like I'm just copy pasting the things which I've seen out here, and I'm just running it out here. So I'm just removing this part because so I'm just converting this frame to image because I should change each and every place image. So I'm just converting here as frame. So if you guys see like you will so you guys can see for image like I am not able to get this image because the threshold values are not proper. So I'm just changing the threshold values out here. Like as it is more wider, I should keep the threshold value something around 200 or something. So I'm just like 150 would be fine. So I'm just I running it again. So I'm able to detect a box, but the box is in black color. So I should remove the inverse function which I've used there. So here I'm just removing this inverse which I'm using here. So I got the box somewhat better. So by just changing the things, you'll be able to detect the box. So I just detected a box. Like I'm detecting this as a mobile because I just gave a variable as mobile, like the text as mobile. So that doesn't matter. So I was able to detect somewhat like, but this will not work for every lighting situation. So like for if I try to detect for a cliff, like I won't be able to detect properly. So for that, like this won't be much good. So now like more advanced things are out there. Like this is all primitive things. Like OpenCV, like all the functions I have shown you are more most primitive. Like now more advanced things have come. Like we are using machine learning algorithms for detecting the features of the image and detecting the object. So with that, you can detect your objects with machine learning algorithms and deep learning algorithms that are available. Like you can also use YOLO and which will be explained by Sahil. So I'm ending my content out here. I'm passing to Sahil. So any doubts? Okay, like someone have asked how it is minus alpha in the convolution. I hope you have got, or like should I need to explain? Okay, like it is nothing but like you're just multiplying each and every elements corresponding to the kernel out there. So nothing but like you're just multiplying each and every corresponding elements out there, and you're just adding summing up. Okay, like okay, I'll just explain convolution once again. Like so, what happens is like I'm just having an image out here. So let this be a 5 into 5 image. Like what's the first step I'm doing is like I'm just having the kernel. Like if you can flip it up and first step is like this how this minus 74 comes is like you're just multiplying this 21 into minus 1. So you'll be getting minus 21 and you're just multiplying uh, 19 to minus 1. So you're just adding minus 21 plus minus 19 plus minus 17 plus minus 71 plus I'm just first doing all the minus stuff and minus 73 plus minus 153 plus minus 164 plus minus 164. And with this, like you'll be getting a value like and adding it with 76 into 8, you'll be getting output as minus 74. So nothing but you're just multiplying corresponding. The first element is being multiplied, the first element out here, and the second element is being multiplied, the second element out here, and you're just adding it up. And you'll be getting the final result for this part to be minus 74. And you'll be just moving it for each and every 3 into 3 cells which you see in this image, and you'll be just passing the values out here. And here, like after doing convolution, your size of the image will be reduced. For that, you'll be doing padding. Like you'll be just adding the extra zeros in the border, and you'll be just doing the same convolution operations to get the same size of the input image as the output image. Is that fine? Fine. So I'm just passing to Sahil.
Hello, am I audible?
Yeah, bro.
So if no one has a doubt, should we move on to the next part? Someone has a doubt in the first part, you can just ask them.
I'm just able to see one correlation. That's it. That's
So
why I
if no one
cleared, bro.
has a doubt,
You can continue, bro.
okay, fine. Is it visible?
Yeah, bro.
Okay, fine. So now that we are done with the part one, which was the features and all, at the last we saw some features like masking and all, but you would have mentioned like how masking works and like what masking is. So we'll start with masking. So basically, what masking is like extracting the part of the image that we're interested in. Like as you can see in this image, uh, like there's a horse and there's a dog and much background is there. So how is it extracting a horse and just a horse and not the human or not the dog? So that is what the masking helps us to do, extracting the things out of the image. So, if we take an example, like if we are building a model to recognize faces, So the only part of the image that you'll be needing is the human or is the human part of the image or just the face. So how can we extract that? There's a so masking helps us in that. Uh, there are many types of masking as we just saw, like Sanjay explained. Many types of masks are there. But what we'll be discussing here would be color masking. So if you ask like why are we discussing color masking? So that would be because in a later project that I'll be showing, I have used color masking in there. So so if I explain color masking now and then use it there, so there'll be a linearity of a level. So as you can see how color masking works, as this is an image of a car with background and road is there. So it's just attracting the yellow part of the image. So how is it doing that? It's how it's doing that. We'll discuss it in the next slide. So we see there. So let's go through the steps of how a color masking works. So the first step would be the importing libraries. So what the libraries would be needing inside Python would be OpenCV that we already discussed, OpenCV and NumPy. What NumPy does is it helps us doing the matrix operations in Python. Uh, Matrix operation in Python. And so why matrix operation is important? Because as we saw that in the image, uh, how computers work is every pixel is given a matrix cell. So the input is in form of a matrix cell. So NumPy helps us do operations with the input pixel. So the next step would be reading the input image. So that would be using the CV2 function that we just saw. Uh, the next step would be the converting the BGR image that we are inputting into HSV. Uh, what BGR is blue, green, red spectrum of the image. Why would we converting into HSV? To so that we would be it would be helping in working with luminance of the image. So mostly how images are like the luminance is very less. So to increases luminance and brightness of the picture, so that HSP helps us in tracking the color of the input image. So the next part would be tracking a particular color. So how we do that is like we define a mask that is a CV, that is a open CV function CV2 dot in range. So what in range does it? So we what we do is like we give uh, a lower threshold and upper threshold of the color spectrum. Like so yellow color is there. So there would be a low yellow color and HSV format. Um, a lower yellow color, so a very light color to a very dark yellow color. So as you can see in this picture, like some part of a dark color and some of a light color. So what threshold does, it's like it helps it extracting all the yellow shades of yellow in that picture. Uh, so after we do that, we create a mask of it by using the CV2 zeros function. And but what it basically does is it fill the entries with to try to track the area of the original image. So now that we have a mask, so this would only this part would define as a mask, not the background. So only the yellow part of the card would be defined as a mask. So how do we extract it from the whole image? So for that we use the OpenCV function bitwise and. So what bitwise and is, it's just if I put it simply, it's this union function as they do in maths. So what it does is like it puts the mask, puts the yellow mask on the original picture, and it does a union function. So every yellow part remains there, and every background or every other thing turns into black, as you can see in the output image. So that is the color masking. So if anyone has a doubt in color masking, so they can put it up. So we can move in to the next part. Uh, is my voice still muffled? Hello.
Yeah, bro.
If my sound is clear or is it still muffled?
For me, it is good. Like I'm not sure. Like it is good for me actually. I guess
So,
please check in your side.
mhm.
Like for the person who asked, like maybe he can check in his side. Like maybe speaker issues. For me, it is fine, bro.
Okay, so we'll do one thing. If you have doubt in this, we'll come back to it later. So for now, we'll move on. So the next part. So now that we are done with mask, so why are we just transitioning into neural networks? What neural networks is like how basically computer vision works. Computer vision works. The backbone is the neural networks. So what neural networks are? They are motivated by how humans perceive the world and are modeled according to the biological neuron functions that goes on in our head. So if you see a neuron, it's basically like if I have a picture there. So this is what a basically neuron looks like. We all know that. So it tries to copy how a neuron works, and so it had dendrites and nucleus. So what is this? It's basically a nucleus, and uh, these are nucleus, and these would be the synapses of. We'll come back to it. So, so the basic definition of neural network is just connected units or nodes, artificial neurons which loosely model the neurons in a brain. So these are connected by edges which model the synapses in a brain. So that would be the bookish definition of what a neural network are. So, uh, is it visible? Hello,
Yeah, bro.
is it visible?
Yes, yes.
Yeah. Okay. So now we go on to explain what basically I would take a very simple example, very real life example of what neural network is. So let's take a scenario. Okay. So this would be a smart guy, and this would be a normal guy like us. So and the goal is to put together pieces of a puzzle. So let's see. Let's put it in the picture of a neural network and how and learn by steps how a neural network works. So step one would be the smart guy will look at all the pieces of the puzzle and try to put together, like try to find a pattern in there. Uh, in the puzzle, like if he sees a pattern on the leftmost corner, on the rightmost corner, so he would try to implement it. So that would basically be the input. So the input he will give it, then what he do step two is he will give instructions to the normal guy. Uh, so especially the normal guy of what pattern that he saw, and then the normal guy would start to put together the pieces. Uh, so it need not be perfect, but you could put any piece to any piece. That would basically be a step in the process of attaining the end product. So that would be processing the data through layers of network. So it need not be perfect. So you can put a corner block to a middle block, and that will happen as a process, and we see. So the step three would be as the pieces come together. So it won't be perfect, but some parts would be perfectly connected, and that would try to that will start to reveal a bigger picture, or like it will be visible like if it's coming through or not. So the smart kid starts to see the bigger picture and make predictions based on the data that is processed. So now that we are very close to the end product, so the most important step in a neural network comes here. That will be the feedback. So so as the smart guy notices the patterns in there, he gives feedback to the normal guy, like see, I see a pattern there. So you try to put the pattern there, leave the pattern there, and try to work on the other part of the puzzle. So that would be learning from feedback. So he'll also see like if this part is perfect correctly. So its nearby places will also be connected. Will start to show a bigger picture. So that would show show that the bigger picture, the puzzle is coming through together. So after this step, what comes is that we go back to step one. That is the smartest again tries to look at the pattern, and this cycle goes on and on until this is fully processed. So this roughly explains how a neural network works. Is that clear? So then we go on to the real working of a neural network. So this is what basically a neural network looks like. So this would be neurons that would do the calculations and all. Real calculation of neural network goes on in the neuron, and some types of neurons like this types of neurons will do one work, and these type of neurons will do one work, and so the they are assigned into assembled into the one picture. So there will be an input layer where the input goes through. So many types of input will there. So like if I take an example, like to determine whether a person will buy a product based on his age and income. So we'll put two inputs like age and income. So age and income will go through, and the hidden layer one and the hidden layer two, that will be assigned to some values. So that will try to arrange it in do mathematical operations on that, and then give out the outputs. So that would be also output layer in this situation. They will be whether he'll buy or not. It won't buy. That would be only the one output layer. So this roughly how a neural network looks like. So if you go mathematically, uh, what a neuron and synapse work through is like mathematically takes the input x. Let's assume that it takes input x, then applies a transformation w. The w would be for weight. We'll discuss it later what the weights are to get the output y. Okay. Here it is z because z will go into another hidden layer, and the ultimate output would be y. So, what would be input x can be a vector or multi-dimensional array. Okay. So, based on a transformation matrix, we get the output to be a vector or multi-dimensional array as a C. So, this structure is further modified by also including the non-linear transformation f. So, I haven't shown f. So, what f is its activation layer. So, we'll discuss it a little bit. Uh, So output. So now we see that output y is not linearly independent of input x, and as a result, the change in x does not proportionally change y. More often, these non-linear transformation consists of keeping all the negative values after applying the transformation matrix W, that is the weight matrix, and the input matrix. So a neuron consists of this whole operation. So this whole operation, this mathematical operation goes on in the neuron, and but synapse is just basically providing a weight. So now that so this is just a layer. Okay, so this will be multiplied by an activation layer. So the importance of activation layer is that why do we use activation layer? So what's the importance of activation layer? Is that it introduces a non-linearity to the function to the neural network. So why do we need non-linearity? So if we don't use non-linearity, so basically it's just mathematical operations, and the output would be of much useful to the end product. So it decides which neuron to activate by how much based on the inputs they get, uh, and the input like the process it goes through, like feedback. The feedback it goes through determines how much to activate neuron by how much. So another thing that it does is it like maps the data to a certain data range. So as you can see in the types of activation layer is that there's one sigmoid function. So it maps the ultimate data to 0 to 1. So that could be 0 to 1 or 0 to some range. So that would be helpful to us to in case of with respect to very random values, we'll plot it to a certain range so that so it's computingly it's easier to compute. So another thing is hyperbolic tangent function. So that is also similar to sigmoid, but it goes from -1 to 1. And another thing, another activation layer is RELU. That is most common. So I would encourage you all to research with RELU as R. That is the most common type of activation layer that we use. So another is softmax activation function. Why have I like put it here instead of putting it here? So softmax activation function is not much used, but sometimes it's used to uh, just before the output layer to convert the output into probabilities that can be used in many situations. Because the output of a neural network won't be perfect, so it will give some probability of what percentage that it will work at. So that is helpful in many conditions. And now that we see, the most important part of a neural network, I repeat again, is the training and feedback function. What training and feedback is basically other name for, you have already heard, machine learning. So what machine learning does approaches to learn these weights and to get an optimal network to start working. So how for that like it needs to perform the desired operation with good accuracy. So for that it needs training and feedback. So for example, we have some cases as we want to do some work like assume if the person is bi or not, as we previously saw, and we give two inputs like age and we give uh, age and like whether he's bi or not, that would be the output. So we have test cases like some people of this age range came and buy something, and so that we have as a test case. So we run these test cases through the neural network, and what it does is like changes its weight and biases accordingly to better suit the situation and real life examples. So in everyday life, how I define it as like we as humans, how we learn from our mistakes. So that is implemented into a neural network of how it learns from the test cases that is already given. So during the learning of the weights of neural network, it is also termed training. The the data set that we input into the neural network goes through layer by layer. That we saw that here it is two hidden layers, but in more complex cases there are more hidden layers that and more hidden layers, and it works more complexly. So for the previous layers transformed according to the layers properties. So what it does is like one layer would have one property, another layer would have some other property to determine. Uh, so that would be the thing. And the final output is a prediction y that we can measure how far prediction. So this only running the test cases won't help. We have to also see that uh, how the test case is different from the actual output. So like imagine if the actual output is 49 and neural network is giving us the output of 44. So how different are those? So different are those? It's called loss. It's termed as loss in the computer network terminologies. So it's a derivative based approach called gradient descent. You can note it down and you can search upon it. But gradient descent is just basic mathematics, nothing more. So then what it does is like updates each weight according to the change in loss and respect to the weights. Uh, so at the end, I have a graph of how it works. Last simple explanation of how it works. So this would be the neural network. We give an input, so it goes. So what it does, the synapse it multiplies by each synapse. The input is multiplied to weight and some bias is multiplied to elevate the number to a certain level. So every number is elevated, so the result won't change. So that's the bias to then be multiplied to an activation layer, activation layer, hidden layers to get a pre-output. So then it goes to the hidden layers, and each node is able to work. So then pre-output is multiplied by an activation. This is the softmax function as an example. So that would be the output activation layer. Then it gives us an output. So that output is then is uh, run through a system of run through actual real life cases, and then we see how difference is there from actual output to the neural network output, and that would be the loss and all. Then we update the neural network accordingly, and then the cycle goes through multiple times to give us output that before we move on to the next part. Somebody please respond. Is it clear or not? Hello, am I audible? Okay, so if it's clear to you guys, so let's move on to the next part. So if I go back to the data network, so this was a tough topic to understand. So uh, a basic neural network is not very hard to understand, but as we step onto the layers, this would be a very basic example of neural network. And as we move up, the complexity of neural networks like increase as that it able to work in like such wonderful conditions and so less time as we saw in as we see in OpenAI's ChatGPT. That would be a very that would be top end example of what a neural network is and how it works. Uh, so if we move on to the next part. So we are done with the report. So now object detection. As Sanjay like explained, various example of object detection like the phone masking and all. That is basically object detection. And to be able to detect the object that is there in the video feed or the image, and to classify it, to remove it or extract it from the background that is there. So, uh, what, like what information basically object detection gives this is it can be classified into four categories. That would be a class name for the object in the image that we saw that it showed a box that Sandeep showed in the video feed, that it showed a box, the name of the box. Or the next would be the object center, like the center of the pixel location of where the object is, or the bounding box surrounding the object that we want to detect in there, and uh, or the instance image where the each pixel is classified into class, and class are for object as well as background. So like the pixel data of every object that is there in the video feed. So how we use object detection? Mostly there are it's used for class name or bounding box. These are the two test cases that are mostly uh, used, and I will also show further as we go into the lecture of how we use the class name and bounding box. But Sandeep also showed it, so that would be a base example for you. So object detection can be broken down into two steps. So there will be two steps to object detection. Uh, one would be to localize the object. So Sanjay took some bounding box from within the data picture as somebody had a doubt like why it is 74. I just saw that example like how he took some part of the he didn't take the whole image, but he took some part of the image and then processed it through. That is basically what is called localization of an image. So we localize the image first. Then secondly, the second part would be the identifying of the image and predicting and showing what the image basically is. So how do they do it? Okay, so how do they do it? You already know that the neural network is the backbone of this of the detection, but there's one step missing in the between. So basically, how its GUI works, like how its GUI works. So I'll explain that. I'll take an example. So one of the most popular object detection techniques that we use now, or that will be used to some time, would be the face detection approach. Uh, like in what we do in IIT is like we have installed some cameras to that recognize your faces and just updates your attendance there. So that is installed in every class. That is a very new implementation of uh, how attendance should be taken. That's very new implemented in IITM classes. So from that, when was it developed? So it was developed by Viola and Jones. Um, and it's in like early 90s and 80s. So I would encourage to you guys. You can also note this point. Like you can research on this. How was it developed, and what was the first steps that they took for developing such a model? So they published a paper which exploited the fact that human face has a strong descriptive features such as regions near the eyes which are darker than near the mouth. So for human skin tone, that is far more noticeable than from the people in this. As you can see for yourself that the area under your eyes would be more blacker than the area under your mouth. So that could be one of the features that exploited to get a face detection. Okay. So there may be a significant difference between the rectangle area surrounding the eyes with respect to the rectangular area near the nose. So that would be breaking the model into geometrical shapes. That would be the easier for the computer to process too. That would also consume like less computational energy. Using this, the several predefined patterns of the rectangle case, they method like computed area difference between the rectangles in each pattern. So as we discussed, like object detection is two-step process. So this was also a two-step process. First, they created a classifier with parameters for specific object detection. For NRT, that would be face detection. And second step that they did is uh, that would be uh, running it through the images that we have. So as we move on to the type of detectors, so there would be two type of detectors. There would be two stage detector and a single stage detector. So what is a two stage detector? Two-stage detector is basically takes more time, but its the output is more reliable than single stage process as in any other computation work. It's going through two steps, so its output is more reliable, but it takes a longer time. So if a two-stage detector is more reliable, why do we use a single-stage detector? That can be a question. So why we use the two-stage detector is that in some cases, like we need reliability more than speed. Uh, like in cases of opening your phone or opening your phone by using camera or uh, some companies use eye detection for opening for some vaults or some other things. Uh, so that needs more reliability than speed. So they have used two-stage detectors, and single-stage detectors are used in more rapidly changing situations like traffic signals, like in some other countries or some places in India, they use object detection in traffic lights, so to see who's following the rules and who's breaking it and needs a penalty. So that would be the difference between type of detectors. Um, is it clear, guys? Hello, am I audible? Like somebody just respond or just put thumbs up. Okay, fine. So we move on to the uh, in this test case, what we'll be doing in this class. So one would be the pre-trained model that you just saw. If you need, like, we can skip this like pre-trained model that subject also showed in there, uh, and one custom data set trained model. Okay, so let's see. It's all based on YOLO V8, but you can use YOLO V7 or V6. It's not much of a difference, but how computer vision is rapidly changing. So it's just like every is dependable. So types of YOLO V8 models we have is like YOLO V8 and YOLO V8 and S and L and X. So what these are is the computational powers of YOLO V8 models. So based on our need, we can use whatever we want. Like we can see like how many flops it's using. So basically, what flops is like floating point operation per second. That is computational power of computer. That is computation like computation speed of a performance, computer performance. That's the condition. So so if we go on. Uh, I do one thing. I've taken one video. So I guess all of you would have watched Mission Impossible. So how is it? The action is so fast paced in there. So would object detection, like a regular computer, would be able to work in those type of conditions, like fast paced action in Mission Impossible movies. So what we will be doing is like detecting the persons in there. Okay. So I'll show it to you guys. So this is the detector. This is the detector like a script that we are using. This is simply like Sanjay would have explained every part of it. So what we are using is like a Euro V8 L model we are using, and the video given the path. So you can also you can test it for yourself on your computer. It's not like much hard to do. So if I show it to you guys. So can you see it? Like it's giving each person like in frame how many persons are there, so it's assigning each human figure ID. So there are three models there, like ID1, ID2, and ID3, and it's also showing what class it's in. In this case it's a person, and you would be wondering like what this number is. So 0.93, 0.92, that is basically a confidence value. So how confidence is the the script like it's recognizing a person, not a wash basin or a dustbin. So that will be conference value. As you can see, it's a pre-trained model. So it's a pre-trained model. That's why the confidence value is so high. Okay, it's gone through much intense, like much greater data sets to train. So you can see like it's very impressive like how technology has come like this far from basic neural network how we can do computation of this magnitude and like a regular computers that we have. So if I stop it, you can try it for yourself. I have given like in the repo I have uploaded all the files of this. So now uh, now we went to the pre-trained model. So I think the explanation of code is not important, but if you want me to explain it, I would be happy to explain. So if anybody wants, I'll explain the code. But it's just basic code. It also I've already gone through. Like you can just put a message if somebody wants to explain the code. Okay, so if everybody is clear with it, so we move on to the custom data set training model. So it's need not necessary. We want we'll be using pre-trained models pre-trained models that are basically trained to so much of data sets and all. Um, we can create our own tailored situation like as I've taken here. So what I've taken is like it's for detecting boxes in a factory-like situation. So that could be a very real-life implementation of computer vision in factory conditions or in like as you see in the airports, like how bags are on the trolley on so they also use this technology. So we'll be learning how to train our own custom model. Okay. So uh, is my voice fine or is it lagging? As you can see, like my connection is pretty poor. Am I audible? Sanjay?
Yeah, bro.
Okay. So we move on to the custom dataset training model. Uh, so I will be doing it on Collab, but you can also do it like locally on your computer. It's not much of a difference, but I've it's like none difference is there, but I will choose to do it in Collab, so I can show it a better. So as this is the piece of code I've already given it to already uploaded in GitHub, so you can access this. But if we move from start like okay, so what I'll do is create a new notebook in Drive. Okay, so until it loads, I'll show you the data set that we're using. So the first important set would be the data set that we're using. So these are the sample images that I've taken. As you can see, it's boxes in various factory-like condition on conveyor belts is there. So how do we use this data set? So for using so first we procure all the images that we want to use. As you can see, I've taken so much of like almost around 100 or 110 images I've taken. So that would be enough for this to work. Then what we do is we train it. Um, so what we do is like first we annotate the images to uh, uh, as you can see like what the images are, like some factory condition is there, and the box is in one corner of the image. So what we'll be needing is like creating a bounding box around it. So the computer recognizes. So this we want the computer to look at and not the conveyor belt. Okay. So uh, that would be the labels as you can see here. That would be the labels of every for each image. There's one separate label. So how we create label is we install. I use a software that's called Label IMG. Label IMG. You can install it in your Python by using pip install label image. Okay. I won't be installing it because I already installed it. So okay, so we started. So this should be the GUI of the label image. So what we do is open a directory. Okay. So there we have a data set stored. Uh, uh, Training images we have. Okay. So as it opens, then what we do is also assign a save directory, where should be storing all the images and the labels that we have. Okay. So then as we go down, there's this thing, a pastel box. As I'm using a YOLO, I would be using this thing. But if you're using any other software, you can create block. Then what we do is create a red box. So what it does is like see, it create a rectangle around it, and we give a name. Like here, like give box. If we create a label for it, then manually we go through each image and we put a bounding box around it. Okay, so that would be the images. That would be for images, and then after that we'll be left with all the labels and images. So we divided it through three parts. For we will do one test, one train, and these are all same folders but with different names. Okay, so that is one criteria that it needs. It needs a test, train, and value. These people. Then there's a doc folder called .yaml file. What YAML file contains is like depending to all the folders that he has. Train, val, test, and this is the skeleton path, and this would be the branches path of it. One main path, and after this continuation would be drive, my drive, which is leading train, and then images in continuation, and then this will be the name of the image that the object we want to identify the image. So here it is a box because I only want to identify only one thing box. But if as you add more objects, you can add more names in there. Okay. So that would be the data.yaml file. Data.yaml file is a very important file in there. Okay. So now we go on to the collab file. So here the first the first process would be connecting the drive. Okay. So you'll upload all these files in your drive, then just connect the drive there. As you can see, it's connected here. Connected. Okay, as you can see, it's connected. And the other thing that you need to look out for is runtime. You can change the runtime to GPU. Okay. As you see, I've put it in CPU. I had put it in CPU, but now I'm changing it to GPU. Why we change it to GPU? Because we need more computational power in this such training conditions. So it reconnects. So first line of it would be uh, like testing whether it is connected or not. So let it connect first. Okay, so whether it is connected or not. So if I run it, so you can see it's connected. It's connected. Okay. So the next line of code, that would something from okay. So next would be installing importing alternatives to our Python. So what alternatives is, the YOLO is a subpart of the alternatives package. So we install the alternatives package, then so we run it. It will take much time. So let it run through. Then the next would be from as you can see, it's automatically generating it. It would be the power of AI and machine learning. That will be separate. So from alternatives we import YOLO. So the next part would be uh, the next part would be ensuring whether we have imported it correctly. So how we do that is you can see this image. We'll be running this image to the imported model that we have and see that if it does work or not. Okay. So okay, I'll show it in the pre-run situation. So as you can see, it has the detections in there. So it can detect the image size. That's a 640 by 480 size, and it has 5%, one bicycle, one bus, and you can see it's pretty very pretty accurate. Like 3% is there, and it's detecting a bus and other things. So that would be pretty accurate for it. So the next part would be the training part. So hello, am I audible? Hello. There is some network issues. Hello. Hello, am I audible? Hello.
Yeah, bro, you're audible.
Is my voice clearer now, or was it earlier?
It's okay.
So, sorry for the. Okay, so where were we? We had tested the imported model, and now we were on the step to train it. So, uh, what is there for train is like we import YOLO, then we put it into the detect mode. The task equal to detect, that would be the detect mode, and the mode will be train. The model that we are using is YOLO read L, the large model of YOLO read, and the data. What data is like passed to all the image training and data set that I showed you earlier, the labels that I showed you earlier. It will be the part to that. It is for me, it's this, but for you, it would be different. So how can we determine that? It's like you can just go go into your uh, go into a like where you have saved it, and just take like just copy the path. Like there's an option for copying the path. Uh, you can just copy the path. So that would be, and after that we have epochs. What epochs is basically how many the greater the number of epochs, the greater the time it will take it will to train the model, and the higher will be the results. So that is what epochs is, and that is there's the image size. That is not much used to determine what that is. So if we run it, it will take much time. So I've already pre-rendered it, so I will show you the results. Okay, right? So this is how it basically looks. So as you can see, it's running through each epoch one at a time, and it will take so much of time. It is not necessary. So what happens after this? So now that we have trained our model, so how can we use the model? Okay, so uh, what it does, it is like save the trained model to this path that would be runs to detect anti-best path. If I we can do this section. So this is this is just basically the path where it's stored at, and we can download the best.pt part. Just make sure you download the best.pt, not the last.pt. Okay, so that would be the trained model we have. So another thing is that you can also see the logistics, like how much is how it's trained, like how each picture is trained, and a various type of graph would be available to use there. It will be of much use if you see and if you can interpret those things. So now that we have trained the file, how can we use it? So this is the folder that I've stored all. So see, this video we'll be using to we'll be working on this video, a train model. So we'll see how it works. Okay. Uh, so this would be the course of it, and there's basically the same thing that was with the pre-trained model. We import all the CV zone function, import the libraries and like the video we import, then the the train model. So what I've done is like as you can see, there's a box one, box two, and box three, and the original model that is based upon. Okay. So what box one, box two, box three is like various versions of train model. The box one was trained on a lower data set. The box two was trained on a bigger data set, and box three is the most optimized that I've used, the biggest data set that I could create. So that would be the box three. Okay, so it's importing the box three and the class name that it will be showing. And these code Sajid has already gone through. If you want, you can just go through it in the recording. Go back in the recording of the lecture and just see for yourself. Okay, so now we run it. Okay, so it's running now. As you can see, it's creating a bounding box around the boxes. So this is the like a blood picture of boxes. So as it is blood, it's not identifying it, but as it comes into a steady and the boundaries are more visible, it's identifying it. Okay. So as you can see, we change the camera angle and then also it identifying it. And as you can see, the confidence value is also very high. That is because I've used the extensive data set that I've used, over 100 images. Uh, I've drawn boxes and we created images. So the The contrast value is very high, like 0.93, 0.92. And this is not given that it will work only in this video. You can also use it on any other video. If you want me to show it work on any other video, you can just tell me. Okay. And even if you want just text, you want me to put it in any other video. If you don't, we'll move on. Just find it. So we move on. Uh, we move on from the custom data model. So now we have the like if you can see like the most interesting part of the lecture, that would be the integration of it with ROS tool. You have recently in the last class only, I think you have been introduced to ROS tool in the Vivo. We'll be introducing open like computer vision with ROS tool. So what we'll be doing, you guys have seen a turtle, right? Uh, you guys would have seen a turtle sim. So what we'll do, we'll be integrating those two, and what we do is the computer, with the help of my webcam, it will be detecting the position of my thumb. So if my thumb is up, the turtle will move in a speed direction. If my thumb is leftward, the turtle will rotate in anti-clockwise direction, and vice versa, as you see there. So what I do first is I run through the code. Okay, I'll demonstrate the work. Okay, so should I show you the code first or the demonstration first? And show you. So what we'll first do is run ROS to Tata Cell. Okay, so we'll run it. So this gives us a Tata Cell, and then we'll run our like I'll run this thumb direction detector. So yeah, show it first, then we'll discuss about it. I guess you can see me, guys. Okay, so okay, so if I move my thumb upwards, like as you can see, it's not perfect, but it's uh, rough showing of how it works. He's rotating, and if I move it other words. So I
So the logic I've used would not be perfect. We can work on the logic. So as you can see, it's moving straight, but sometimes it moves. If I put my thumb down, it stops. It's like somehow stops. So okay, so okay, sorry. If you want me to let's see the RQT graph of this. Can you see it? So these rounded objects you would be knowing are the nodes, and this is how it's contacting the each nodes through this rectangular box. Okay, so that would be the message type. So this is my node. These two nodes are created by me, and all these two nodes and this uh, message file is created by me, but except this, everything is related to turtle sim, and how it's contacted to turtle sim, we can see that. So what thumb direction detector is doing, it detecting the direction of thumb, then it's publishing the data, and the ROS control node is subscribing to it. Then it's contacting the turtle sim CMD well. What is showing is like it's publishing uh, the operations that it wants the turtle to do, and CMD well is subscribing to it. Then it's contacting the turtle sim to it's giving a message to the turtle sim to move it, to move the then the turtle sim is contacting the turtle to move it and update its pose and status, and it's also giving a feedback. Okay, so that would be the architecture of explanation for this one. So if I close this, and if you want if you want to see the if you want me to explain the code, we'll go through the code now. So what this is the workspace of a ROS. You would have seen that for ROS applications to work, we need it needs a specific workspace. You can see here also I've if I go at the starting, so I'm going into my workspace, the source folder, and the package. I'm going completely into the package, and then I'm doing the callcon build. I'm building the package, building the workspace. Then I'm sourcing it. So for every terminal, we need to source it for ROS to work. If we don't source it, the nodes won't work in the terminals. So that would be it. So if I navigate you through the workspace, so as every other workspace is divided into four this build, install, log, and all the codes that we have done would be in the source. Okay, so if I go into the if I go, there will be a package thumb control in the source folder. So if I go into the thumb control, and there would be another folder inside thumb control that is also named thumb control. If you see like many examples, you'll get to know how a structure is built in a ROS workspace, and this is a very uh, it follows the that criteria. Okay, so if we go into that and we go into log, we'll get the various folders that we have, and this is a setup which we like these two nodes that we have created. Uh, all these files are uploaded in GitHub, so you can access it whenever you want. I know it's a bit tough, but you can access it later and try to learn it. Okay, so these are nodes, and and we go into the package XML. So that this will be all the dependencies of that we have used in creating nodes. So the RCLPy is the default ROS2 package. Then the sensor images we updated, and most important is the CV bridge. So if I introduce you to CV bridge, what CV bridge is creates a bridge between the compute OpenCV and ROS. Um, the OpenCV will be publishing its messages in one type file, and ROS will not be able to like subscribe to those type files, and there's a bridge gap. So what it does, creates a bridge between those and converts the OpenCV files to ROS, or ROS inputs to OpenCV. Okay, and this is just the OpenCV. Okay, uh, so now we go into uh, the files that I've created. So this is importing all the necessary, the NumPy I've told you, like CV, OpenCV, and some detector. Okay, so as you can see, this line of code, what it does, it's like creates a string. It's publishing a string, like a string data type to thumb direction. Uh, it's publishing, and this is the video capture, like the webcam that you saw, and this was explained all by Sanjay, like in the this all this basic uh, basic things of of a detector. Okay, so this is the main algorithm that I use to detect the thumb. So what this is converting the BGR to HSV, and here I've used. Okay, so we discussed the color mask. So that is the what I'm using here. So this is the lower skin color threshold and the upper skin color threshold. I've set it to the human skin tone. The human skin tone in India. Okay. So if you want to use it on uh, uh, like Western people, it not work that efficiently. We need to change the threshold in some range. Okay. So then it creates the color mask of color mask around my body and around the skin colors that is detecting in the image. Okay. Then I'm playing a Gaussian blur of 5 by 5 5 by 5 uh, matrix. So what it does, it's like it helps in detecting the objects in the image more proficiently. You have seen Gaussian blur earlier. So then it creating a contour like a 2D a binary image of whatever the skin color it's seeing, it's giving it a white value, and the rest is black. So that is also it is saw. And so after we apply the contours in the image, there will be many types of contours. As the system is not perfect, it will detect a major blob, a major uh, me like my skin blob. It will detect, and some nitpicks here and there it will detect. So what we do is that we iterate through every contour that is detected, and based on the area size, it arranges into the descending order, and we go then we go for the top two or top three uh, areas of the image. Okay, so then then for detecting so after we have detected the skin color, what it needs to detect is my hand. Not it won't detect my it need it for this software, it won't need my face, so we can remove the face. So but how will we remove the face is using the hull feature. So what a hull feature is, it sees for the like defects in the shape, like as in finger. There's a concavity between each finger that we have. If you see your hand, like between each finger, there's like a shallow region. That is what we call as defect. Okay, the defects is convexity defects, and we won't need we only need the convexity defects, not the concavity defects. So that would be the convexity. It's like the inwards defects it will recognize. And if the end of the convexity defects is more than three, if you see here, uh, more than the like, see the hull is detecting. If the hull is more than three, which in a hand we have five hulls. Okay, so if the hull is more than three, it will detect that it's a hand, and it will take that as a uh, it will take that as a uh, as the object for of the object of consideration for the next few steps. Then then we go through the convexity defects and we count the finger. So if the defect is not none, if the defect is none, that means we haven't recognized a hand, and we need to go back to the hull alpha and identify it again. So if the defect is zero, that means we haven't identified. But the defect is not zero, then we can proceed to the next few lines of code. So this is SEFD. You will be asking what is that? So those are the top of the finger, middle of the finger, and the bottom of the finger. For each finger, it's as you can see, it's iterating for each finger and then calculating the angle the convex defects makes. Uh, like the A, B, and C would be the angles that it creates. We need not go into the details, but if you want, I've handwritten notes of what each line of code does, and I'll share it to you later. Okay. So it creates an angle, and the angle is less than 90. So as you can see, the angle between our fingers won't can be greater than 90. Okay. So the angle is less than uh, so this would be like um a cautionary step. We've installed so many cautionary steps here to ensure that the code is working fine, and uh, we'll see like if the it will increase the finger count, number of fingers it there. So we assume, so after this we don't have the necessary means, or I haven't found the necessary means to identify to differentiate um, a finger, a regular finger from a thumb. So we assume that whatever the finger it has shown, it's a thumb, and we proceed to the uh, like proceed to the code that I've cooked up like here. So for left and right, this is the, so what it does, it's like it creates goes to center, it detects the center and center of the hand and center of the thumb. Okay, so if the center of the thumb leftwards to the center of the thumb palm, it will show that it's left, or otherwise it will be right. Okay, so and up and down also is there, you can go through the then we go into the main feature that is not much, and is there like a regular in every node that you can see that we are, this is the function, and then we are calling the function in the main, and to stop it also we have put it here. Okay, if you have any doubts you can just raise your hands, I'll take the doubts. Okay, and so this is the publishing the string, but who's subscribing to it? So this is the node that is subscribing this piece of code that you can see that is subscribing to the string, and then it's also publishing the twist message for the turtle sim to subscribe to. Okay, so this is the moving of the turtle. So depending on whether the thumb is up or down, it will give the linear velocity or the angular velocity to the turtle. Okay, then we have main function which is calling the function and all. Okay, so we are done with this. So if anyone has a doubt, you can just ask. If you want, when will the session will end? It's just we have just completed with the session, and if somebody has a doubt, so please send these files. Okay, so as you if you go into the summer session group, there will be a session 6. Like links would be there. So I've uploaded everything in GitHub, so you can access that. Uh, and uh, and the image, and then the image I have used also, that also I've given the drive file for it, and you can just access those. Okay. If somebody has a doubt in any session, like in the session or my part, or uh, Sanjay's part, so you can text.
So yeah, it's already late. Like we'll just we have just come to the end of the session. So I hope you guys found it useful and learned about how to use computer vision and robotics, and you just saw the applications. Like maybe you guys may not be familiar with ROS, so maybe like, we'll be sharing few resources with which you can, if you're more interested in it, you can learn it. So we'll be sharing a PDF of resources soon, and we'll be sending the assignments. So that's it,
Yeah.
guys.
So so how was the session? Okay. So are some people not in the WhatsApp group or not? Like, okay, so we'll be wait 5 minutes more maximum. So if somebody has a doubt, you can put it up in text or just unmute themselves and ask. Then we'll end the session like 5 minutes. Sanjay, did you take the attendance?
Yeah, bro.
Okay, fine.
Attends. So shall we end the session?
If nobody, somebody asking for the WhatsApp thing, like,
Yeah,
just share it. Share it here only, the WhatsApp group thing.